All right, let's talk a little bit about using derivatives to find maximum and minimum values. Now, the first thing I want to look at sort of a quick example that kind of goes behind the theory or a little bit of some of the rules that might seem kind of odd at first. Kind of just explain sort of what the reasoning is behind it. Let's say you have some line or some graph like this, and you have this point A and this point B. Now you're looking at this interval between A and B. And if you have this is called open. If it's open between A and B, technically you're not going to have a max and a min value. And that might seem a little bit weird, but the reasoning is because you actually don't land on a value. This line is going to get infinitely close to B, but it's never going to actually reach B. So like let's say you did B minus 0.1. Or you could do B minus 0.001 or B minus 0.000001. So you could always add one extra zero. So there is technically an infinite amount of numbers like getting close to B, but not actually landing on B. And because it never lands on a point, that means that there's no point that we could say, well, this is the definite max value. And so that's why if you're looking at these like a line like this would have no max and no min because there's no value that it could land at. Now let's say it's open at A but closed at B. Then okay, well you'd have no min, but you'd have a maximum value. Right? It's dependent on each case. Right? So or the best case is if it's closed and bounded on both sides. And in that case, then you know that there would be a max and that there would be a min. So just kind of keep that in mind. There's some other rules that the book goes over as well. But that's one that I always, when I was going through calculus, I was sort of like, that seems kind of weird. So that's the reason behind it. All right, now let's take a look at what exactly it is we're doing when we take and use derivatives to find these max and min values. Let's say let's just kind of draw some random. Let's say you have a function that kind of goes like that. So what we're going to do is we're going to find, or the points of interest on this line are going to be where the derivative is equal to 0. All right, so probably right there is going to be one. And because the reason why we're interested in that is we know that where the derivative equals 0, typically, now, not always. If this went down and then over and down, then the derivative would equal 0, but you wouldn't be a max or a min value. So, but typically when it equals 0, it shows that this is going to change direction. You can think of it sort of like if in those physics experiments, if you threw a ball up in the air. So let's say you throw a ball up in the air. There's going to be an instantaneous point when it's totally weightless. Boom. And then after that point is when it's going to start to fall down. Well, we know that the point when it's instantaneously weightless, when the derivative is equal to 0, like it's not change, the rate of change is not changing. Well, we know that it can't get any higher than that. In physics example, it's because it's out of velocity, right? The acceleration due to gravity has overcome the initial velocity upward, so there's no more oomph to propel it up. So that's as high as that object is going to get. And so because these are so useful in finding maximum and minimum points, we call these critical values. So it's important that you investigate the critical values once you figure out what they are. But we're going to use derivatives to actually figure out what they are, and then you can either look at them graphically or analytically. So let's take a look at a real quick example. Oops, that kind of got all crazy. There we go. All right, so let's say, well, we're going to take the derivative, so go ahead and write that out. How about let's do x plus 9 squared over x squared plus 9. And what we're going to do is we're going to set that, when we find the derivative, first we got to find it, then we're going to set it equal to 0. All right, so let's get to work at this. Looks like we're going to be using the quotient rule, so this is going to be f on the top, and this is going to be g. So let me come down here. We're going to have f prime. So the derivative of this looks like we're going to want to use the chain rule. So we're going to have 2. This will be our u. X plus 9 will be u. Just rewrite that. And then so we'll have 2u to the 1. So we just leave it as is. Times the derivative of the inside, which is just 1. So, all right, we don't really have to do much there. So we're just going to do multiply it by g, the bottom one, minus, don't forget the minus. All right, then we're going to have x plus 9 squared times, so that's f times g prime. All right, looks like this one we can just do straight up. It's not a composite function at all. So derivative of x squared is 2x, derivative of 9 is 0. This is all going to be over g squared, or x squared plus 9 squared. Okay, so this is going to take a little bit of algebra. Let's focus just on the top. So this is kind of just going to stay as is. But on the top, let's try to simplify this out just a little bit. So just on the top, I'm going to have, we'll leave the 2 alone, and then let's FOIL this out. So I'm going to have x cubed plus 9x squared plus 9x plus 81. All right. Then minus, let's bring this 2x to the front, and then we're going to FOIL this. So I'm going to have x squared plus 18x plus 81. All right, again, I'm not going to write the bottom because we've got our work cut out for us. We're just going to figure out the numerator first. So, okay, let's multiply this through. I've got 2x cubed plus 18x squared plus 18x plus, 2 times 81, 162. All right, and then don't forget this minus sign. This minus sign goes with the negative 2x. So I'm going to have negative 2x cubed minus 36x squared minus 162x. All right, so far so good. Now let's see how it simplifies. I've got, well, this is kind of nifty. My x cubes, that's going to make our life a lot easier. So I've got my x squareds is going to leave me 18 minus 36. That's negative 18x squared. I've got 18 minus 162. So that'll be what, 144. All right, and then moving on down, looks like there's nothing to do with that, so 162. All right, we're getting kind of close. So let's go ahead and take this. Do that. Looks like we can divide everything by negative 18. So let's bring that out to the front. So I've got x squared, 8, and then minus 9. All right. Good. Now we're really looking good here. So all I'm doing is I'm looking for negative 18. Two numbers that multiply to negative 9 and that add to 8. Well, 9 and 1 does that. So I know that 9 minus 1 is 8, and 9 times negative 1 is negative 9. All right, now we're in business. Okay. Over, don't forget, x squared plus 9 squared. Okay, so we found our derivative. There's our derivative. Took a little bit of legwork, but that's okay. And we set it equal to 0. All right, so now what we're going to do is we're going to solve for x. And this is pretty easy with how this factored out. Some of them can get a little bit more complicated. But I know that when x equals negative 9, or when x equals positive 1, that derivative is going to equal 0. The reason being, if this is 0, it doesn't matter what these other two things are. 0 times anything is 0. And the same thing with this one. So I've just set each of these equal to 0 and then solved for that x. Now, taking a look at the bottom, we don't have to worry about the bottom because if x is negative, or yeah, if x is negative, it's going to come out positive anyway, because we have the positive value. So this is always going to be positive, and even more so, this whole thing is squared. So we've got a lot of squareds in there, which is going to guarantee that this is positive. So we don't have to worry about this being 0 at all. All right, so we figured out where our critical points are. Now, what you could do from here is say, okay, well, let's figure out if they're max or min by just plugging them in. Right? Let's see. We've got, oh, well, this first one would be super easy, -9. Right, so -9 up here, that's just 0 squared. So this is our first point is going to be -9 and 0. Our next point is going to be 1, so that's 10 squared over 10. So 1 comma 10. All right, so you can use that to sort of figure out, but it's really nice to be able to see what the graph is doing beyond these values. So let's just take a real quick look. This is one of those things where having access to a graphing calculator is something that is extremely helpful, and that can save you a lot of calculation in the long run. So let me see if the hardest part of this is just typing this in right. Okay, so this is x plus 9 in parentheses squared over x squared plus 9. All right, moment of truth. This is also kind of nerve-wracking because, hopefully we did it right. All right, so here we go. There's our graph, and here's our first point. Oops. There's our first point. It looks like we did it. Here, I'm just gonna, let's say this equals y. Y equals this. I think it should. Aha, there we go. All right. So, there. Okay, good. So 1, well, all right. We'll just call that rounding error by the computer. But our first point, 110, looks like it's going to be, this could be the as high as we'll ever get, because it looks like it kind of goes back down. And then this other point, I think it was -9 and 0. Let's see if we can't get it to. Yep, right there. And you see how it kind of dips down, hits 9, and then starts going back up. So this would be a minimum value. So another way that you can do it, this is, just for fun, if you kind of want to see, you can also graph the derivative. So let's say, give me 1 second to find it. There it is. Okay, so we had -18 times x plus 9 times x minus 1, all right, over x squared plus 9 squared. Whoops. There we go. All right, and that's kind of cool looking. Yeah, pretty neat. So what we do here is, this is the graph of the derivative. So you can see how it kind of follows, like at this point here is where, you start going from this, and where it starts kind of slowing down. There's a lot that you can tell from the graphs of these derivatives, but what we're going to look at here is, you see wherever it crosses 0, wherever that graph crosses 0, that's going to be one of those inflection points. So it crosses 0 there, so we know at x equals 1, or also back here, we'll trust our math and say that it's going to cross at 9 or -9 right there. So this is, you can see this would be really, really easy. You can go fairly quickly if you just use graphing. But also, just keep in mind, though, make sure that you know how to do it on the exam, that you can do it analytically. Because you never know, like, on the exam, if your graphing calculator, I don't know, something happens, or it's just important that you can do it analytically and then use the graphing calculator sort of as a way to check, the work that you did. But that's kind of the gist of it, taking the derivative, setting it equal to 0, and solving for x, and then using that information then with the graph to get a bigger picture of these max and min values.